All right, let's make a start. We gained a table on the stage, which is not entirely useful for this session, but anyway, there's a table. So this is the first of the two APOPS sessions. What APOPS is, the Asia Pacific Operators Forum. What the program committee does when we develop this is to put the most interesting and most relevant presentations for the whole community in these two sessions. So we have 3 presentations today. We've got 2 presentations tomorrow morning's session. So I think I'll just start this off by giving the floor to Jeff.
And the mouse.
You want a mouse? Why do you want a mouse?
Well, the thingo.
Bingo.
Thank you very much. I'm Jeff Houston. I'm with APNIC. I'm their chief scientist for Grand Sand. I do a lot of measurement and a lot of looking at the network, partly because it's really fun, but partly because certainly in APNIC, in terms of address policies, part of our issue is we really don't want to create policies that completely stuff up the routing system and blow up the network. Like I'm just right there. If you've got a laptop, turn it on and have a look. It's not even connected. Guys, I just pressed advance. This is really exciting. Okay, now I'm really going to race through the slides once I ever get it up, and I'm sorry for this, but it's you know, it's fine. It's on YouTube. We're okay. Great. The next slide is visual, right? It's visual. I can't talk it through. It's a graph. It really doesn't work unless it's up on the screen. Control-Alt-Delete, off we go. Yay! Routing gives you this amazing picture of the business of the internet. Because oddly enough, when you feel like there's money around and you're building your business, that actually translates into routes in the routing table. And when the big bust comes, as it did in 2001, and there was even a kind of a correction going on in 2009, you can see the scale drops down. The routing system actually reflects the underlying business of the internet. And I must admit, in the year 2000, we thought this was the big grand boom time of the internet. We'd gone to, whoa, 100,000 routes. And if you look now, we're hitting 700,000, and the slope is even bigger than that. You know, it's just gone gangbusters. Because I'm not sure any of us truly understood what consumer marketing was all about. We just thought we were geeks. And when consumer marketing came along, it just took over everything. So this is the last 18 months in detail. And now I've taken a subtly different view. I've looked at every peer in route views. Every single peer is a different colour. So when I do a map of Kathmandu on Apple Maps and a map of Kathmandu on Google Maps, if I really look hard, they're a bit different. And oddly enough, BGP has the same issue, that not everyone sees the same internet. And that not everyone is actually almost up around 50, 55,000 routes. And interestingly, the Europeans see fewer routes than the Americans. Don't ask me why. It's some kind of Atlantic thing, right? That they just see less than what's going on in route views, and that's predominantly the American route views, route peers. Average growth across the last 2 years, linear, not exponential, not flat, linear. So here are sort of some things to sort of tell you a bit more condensed up, because it's a lot of slides and it just gets a bit dull. We're growing at about 55,000 prefixes a year, and it's basically a steady linear growth. What does that mean for your route of table size? It's pretty stable now. You can predict 5 years out the kind of things you're going to need in hardware to make the internet work. What is stranger is the one at the bottom. The number of new networks that appear as AS numbers has been at 3,400 prefixes a year forever. Now, I don't know how you do it. It's kind of like it's your turn to announce an AS, it's your turn, it's your turn. You all seem to line up, but I'm not sure where the counter is. I'm not sure why it's not seasonal. There's no break for Christmas. It's just a steady, constant, basically 10 a day. Forever. Aren't computers wonderful? I've no idea. Will someone stop rocking that? I won't look at it. It'll make me seasick. I don't know about you guys. More specifics. And it's always been this whole issue that the vandalism in routing is actually advertising more specific routes of aggregates. This has always been senseless routing vandalism. The scale doesn't matter. The fact that it's flat as a percentage means that we're not getting any smarter, we're not getting any dumber, but we keep on routing more specifics every single day. So the more specifics, it's a little bit over half of the routing load, doesn't actually add to reachability. It's all about traffic engineering, and nothing's changing. This is the one that I was sort of getting to. We ran out of V4 addresses years ago, and progressively over the last, it's been since 2011, 7 years, we've been running on empty. And the only way we do that is to make the size of each routing prefix smaller and smaller and smaller and smaller. And that's what you're seeing. That red line just keeps on getting smaller and smaller and smaller and smaller. We refuse to give up our addiction to V4. Totally refuse. And in the light of there's no addresses, okay, I'll just take one address. And we're getting down there to an awfully small average routing size, and you kind of wonder when someone's going to be brave enough to try and advertise a /28 globally. The time is coming. It will come. There's the total amount of address space, and you see it sort of curving off because we don't have any more space. And the next one, the crowding cluster. In topology terms, none of you like to be a customer of anybody. When you bring up your new network, you try and drive as close as you can to the largest provider you can see. So for Nepal, Heaven is not connecting to an Indian ISP for transit, but driving a circuit all the way to one of the tier 1 ISPs or tier, 2 or 3 of them. Bring your AS very, very close into the center of the network. The average AS path length of every single prefix is not getting longer. It stayed about the same. So if you think about this as a sun, we're increasing the density. We're getting to neutron star base. That the network isn't getting bigger, it's getting denser. Because as we grow all those routes, the average diameter of the network remains exactly the same. That's a good thing, and we're going to see why in a second. So this is the AS adjacency distribution. Only 20 ASs have more than 1,000 adjacencies, and that's the top. Those folk are the internet. Everyone else are hangers-on. If you see yourself there, good on you. Hurricane's here somewhere, well done. But that is kind of the adjacency, and the spread outwards, almost everyone else out of 60,000, 43,000 are right at the edge. They only have one upstream. So the network's very dense and very clustered, and that's been the same way for years. So address exhaustion hasn't really changed any of this. Your routers still need to get bigger. The number of entries is still growing. The pace of growth is around 53,000 entries a year and 3,500 ASs. If you're building hardware, you could probably build hardware for 8 years out and you wouldn't be much wrong. We know where this is going. Why? I don't know. Why are those numbers so regular? I don't know. But the observation is that they are regular. So what about address exhaustion? Well, we're getting there. We really are draining the swamp. There's almost very little left. Aaron is relying now on addresses returned and addresses given out. There's no pool left. Afrinic, the best estimate right now, June 2019. That's coming. It's only, 16, 17 months away. LACNIC, the residual amount of addresses they have now will last again until September 2019 because they give them out, one a month or something. It's a really slow burn rate. The RIPE NCC and APNIC, each of them have got a couple of years to go. They're in that last /8 where everyone gets 1,000 addresses. And so there's no need to panic. There's still some left. But in a couple of years, there won't be. It just won't last that much longer. And that's our best estimates as of a couple of weeks ago. So what are we doing? Because there aren't more addresses. The addresses we're handing out are tiny. So what I did was I took a snapshot of the routing system at the start of the year and a snapshot at the end, and looked at the addresses were added, and I looked at their age. So in 2010, which is this distribution, 80% of all the addresses added in 2010 were handed out in 2010. In other words, we gave an address out, it got routed. Almost none of the addresses that were added were very old. This is every year since then. And each year, the number of addresses that, if you will, were given out that year gets smaller and smaller, and the big black line is last year. 25% of all new addresses that we saw in the routing system, just 1/4, were allocated that year, predominantly from Aphrodite and bits from Ripe and Apenic. 30% were mining our history. They were mining all those legacy Bs and Cs from yonks ago that we're basically pulling out of the dim, dark, dusty cupboards and returning them back into the routing system. Interestingly, 2016 had the highest amount of history mining, and 2017 has gone back again. There is a suspicion that at the current price, we've flushed out everything that's going to flush. If you want more addresses out of the old legacy tables, you need to look very carefully at how much money is in your wallet, because the only way you're going to flush out the rest is by upping the price, because those figures are showing the existing pricing structure isn't freeing the addresses off at the rate it was before. The folk who are holding it are holding out for a higher price. Addresses are getting more expensive. So I'm going to build 3 numbers, and I'm going to change them in a different way. The blue line is the addresses that got handed out from the RIRs into the internet. The green line is the addresses in the routing system. The gap between the two is the red line, the addresses we handed out, but I can't see them. Yeah, so you can see address exhaustion, they're kind of standard curves. But what if we just look at the red line and blow it up a little bit? Since we ran out, we've reclaimed the equivalent of, got to look at the scale here, around 5/8s. Not a lot. There's an awful lot still left, but I think they're price sensitive. You're going to have to pay a lot more than what you're paying now to free off the rest of those addresses. Sorry. Let's also put this a different way and just look at 2017. I don't have a lapel mic, but maybe I'll shout a bit. Oh, the growth in routing addresses is green, okay? So that's the growth of the routing system, but the blue line is the allocations we handed out. So what's that? That's the reduction in the unadvertised address pool. So in other words, what we're able to do across this year is you can see the extent to which the market has steadily, day by day, started to drain those old pools of addresses and lift them into the routing system over and above what the RIRs are allocating. And so the summary of all of that is that we allocated 0.8/8, that's what, 12 million addresses, and the rest, which is around 9 million addresses or so, were actually recovered from the legacy pool. And as I said, because the legacy pool is finite, because the folk who have addresses are price sensitive, if you bought addresses last year, you paid less than if you're going to buy them next year. And that's just scarcity economics. Brutal but true. That was V4, this was V6, time is marching on. This is an exponential curve because V6 is just gangbusters, right? We always thought that when we ran out of V4, you guys would just do V6. We are completely and totally wrong. That's when you ran out of V4 and nothing happened. So yet again, you prove us completely ignorant and silly. We're sorry, we didn't get it right. Yeah, tough. Here's the last year in detail. And if you thought that V6 was different, you're kind of wrong. That what's going on is that the range of what we see in 6 across each of the providers is also different. You don't care about default. You don't care about seeing the same route system as everyone else. In fact, I'll make a further bet. You only care about getting to Google, Amazon, Facebook, and LinkedIn. And if those 4 routes are in your routing system, you don't care about the rest. Because no one's fixing up. Those folk down there don't feel left out. And these folk up there don't feel that they've got too much. No one cares. Only 4 routes matter in today's internet, sadly. Here are the indicators. We're growing, not by any mere extent of V4, but 50,000, no, it's only 10,000, but it is growing. AS numbers, V6 is not growing as fast as V4 even today. Half the pace. Instead of 3,400 a year, only 1,700 a year. So whatever the V6 message is, only half of you are listening. The other half are asleep. Sorry about that. Wake up. More specifics. Well, if more specifics were fun in V4, they're fun in V6. So senseless routing vandalism is kind of infectious and everyone does it. And even in V6, and it was really hard to represent this, so I had to go logarithmic prefix size, but believe me, it is getting smaller. So these buckets of address space, and I can do anything I want, people are advertising smaller and smaller prefixes. I think you have a mindset about routing that we can't change. There are tons of addresses. No, I must route /2127s. And I just can't stop you. No one can stop you. You're a machine. Average address span, it's just growing at a linear rate. And interestingly, the same clustering in 6. None of you like being a customer of anyone else. The average AS path length is actually getting smaller. The clustering is getting bigger. Who's big in V6? 10,000 out of 15,000 ASs only have 1 upstream, 1 or 2. So that's the edge. Only 5 have more than 1,000 adjacencies. Only 5. So who's the backbone of V6? These 5, because they have all the adjacencies. Telia Seacom Level 3, Cogent, and Hurricane. Hurricane has, double everyone else. So, they seem to be right in the middle of what adjacencies are all about. I compared the V4 and V6 trends in terms of the overall distribution. It's much the same, but smaller. So the same patterns of business. It's just business. If I'm your customer in 4, I'm your customer in 6 if I'm doing 6. We're not making new relationships. So, overall 10,000 a year, I'm going to go faster. What to expect? Well, quite frankly, this is all numerology. There's no science. I'm just taking the numbers and pushing them forward. There's the daily growth rates, 140 routes a year. Pump that through, I get that number. By 2023, in 5 years' time, if you've got your line card with a full fib, and I'm not sure why you want it these days, because only 4 routes matter, but if you want the rest anyway, because you just feel like paying your favourite routing vendor, you're going to need at least $1 million in your fib, just for 4. Just for 4. And don't forget, in 5 years' time, it's not 100 gig, it's a lot more than that. So it better be really fast, really big memory. Get your checkbook working. Vendors, put a big smile on your face. What can I say? V6, growth rates are a little bit more tougher, and it's hard to say whether it's linear or exponential. But certainly the predictions are out there that an exponential growth is believable because the numbers are so small. It's only 194,000 entries, even in 5 years' time. So it's more likely it's going to be exponential. But again, if you think about line cards, even though, in theory, you're not meant to use /128s, how wide is the fib in 6? It's 128 bits wide. So these things are the equivalent of 800,000 V4 entries. So at some point in the next 5 years, when you start thinking about scaling your line cards and carrying a full route set, you're either going to go, oh my God, it's too hard, or you're going to need the equivalent of 2 million 32-bit entries. Because in 5 years' time, that's what you're looking for. And if you're only buying a new router every year, you're nuts. You need to make these things work in the field. So those are the kind of numbers we're talking about. The routing table isn't going to melt, BGP isn't going to melt, things are just fine. What about updates? And I'm going to go really fast. Update rates defy gravity. The updates, that's the size of the network keeps on growing, But the number of withdrawals, constant. Even the number of updates per day is not very high. So oddly enough, the same old IBM PCXT that would work 10 years ago will still run BGP. You don't need a huge amount of compute power to do BGP updates. BGP itself, this is the time for convergence. Way back, 2001 or something, it took on average 45 seconds to converge. Yesterday, it took 50 seconds. This road system out here, as soon as traffic hits it, it goes slower. BGP has had 1,000, 1,000,000 times increase in the amount of size and scale, yet its performance has remained linear. Whatever you're doing is fantastic. No other system on this planet has that scaling property that it can scale to that astonishing size and still hit the same performance levels. That's amazing. What's worrisome is we don't understand why. Whatever you're doing, for God's sake, keep doing it. Just don't change, because it's the right thing to do. And if you're thinking of doing something else, the problem is you might bugger that up, and that would be a bad thing, So conservatism in routing kind of pays off. So the updates, not a great level of concern, we're doing fine. V6, wow, this is the bit where things go a bit wild. The routing table's growing, but the update rate has gone completely lulu. Completely lulu. And if you look at the convergence performance, that's the V4 50-second rate. The average in 6 is just all over the floor. This is not a good network. And it's kind of difficult to understand what's going wrong, but here's a clue. There are about 30 people out there in V6 routing land who are insane. And they don't understand stability in BGP. And those small number of people, the 1%, do almost 99% of all the updates. Who are they? They're these people. Thailand, Laos, Thailand, and Singapore. You're in the room. If you're in this list, you are indeed insane. Stop it. Whatever you're doing is insanely wrong. Look at the number of updates. I couldn't even do that if I tried. And I know a lot of BGP, but I couldn't do that. So whatever you're doing, it's brilliant, but for God's sake, don't do it, okay? Because as soon as you stop, this will look better and that will look better. So, clean up your act. Routing futures, as far as I can see, BGP is BGP, and BGP isn't going to change one iota. It's scaling like crazy and it's doing just fine. The fib size, I think, is a big issue. And it would not surprise me very, very soon if you start to see pressure to do really small fibs fast and larger backups in some kind of cache system. Because as we keep on trying to make every single packet treated the same, the costs are going to balloon out. And if all you really are, you access networks, is Google feeder networks, you only ever need one route in your fib anyway. The rest are just there for jokes. So, at some point, the fib size issue is actually going to cause the vendors to rethink, because we cannot keep on building ultra-fast memory with the kind of size and speed requirements that we want for gig fiber and stuff that into every single line card. Or maybe we can, but you can't afford it. One way or another, I think that's going to break, and it's going to break in the next few years. And you are going to see a complete change in, if you will, performance of high-speed routing versus good enough routing. And the thing is, as long as you keep Google in the high-speed cache, nobody will notice, because there's no traffic to anyone else anyway. So, some practical suggestions. If you run routers, do understand your network and your network's fib capacity and understand where your options are. You really need to review your V4, V6 partitioning as V6 comes up, because the old rules don't work anymore. You have to constantly look at how much of the fib you're allocating to 6, how much to 4. And over the next 24 months, absolutely. You might really want to consider cutting out routes inside your network. Start doing more and more work with default and push stuff right to the edge, because carrying full fibs all the way through the internals of your network, is kind of a yesterday solution. It ain't going to work no more. Wow, half an hour. Cool, thank you very much. Got any questions?
I'm sure you have lots of questions for Jeff. No questions? Yeah, so if you can please use the mic and just sit, yeah, the mic, and because the session is webcast, so that the folks who are watching can hear what we're saying. So just say who you are and so on.
It's on?
Yep.
Good. Let's see. You made the comment about V6 AS relationships being the same as in V4. And I would say that there's obviously some similarities there, but there's going to be a lot of differences. There's a couple of, there's one aspect that makes the V6 and V4 BGP or routing tables different is that, I don't know what the number is these days, but it used to be about 80% of the ASs that exist in the routing table for V4 just don't appear in V6. And maybe that number's changed. But you also see like Hurricane Electric will show up as a transit provider for a lot of things that they in V6 that they're not in V4. So there's, I don't know. I would push back on the notion that the relationships are the same.
Can you push this slide up, please? I have my slide here. I want it up on the projector. I want to answer your question. Okay. And it's not about specifics. So it's not about this AS or that AS. What I'm actually talking about. God, YouTube. Hello, YouTube. Yeah, right. What I'm talking about is the slope of that line of relationship where so many folk have 5 peers, so many folk have 8, so many folk have 10. That slope is the same as the V4 slope, only lower. It's not a different shape. So the clustering that happens in 6 is the same pattern as the one in 4 with just fewer ASs.
Okay.
And that's kind of what I'm saying about there is a small group of folk who live at the centre of 6, the same as that small group. It's in grey, so it's harder to see, but there's a small group of folk in the centre of 4. And the trail is the same trail. And then you get everyone else down there with 1 or 2 relationships.
Sure.
And that was kind of what I'm referring to.
I got it.
This is what makes scaling in routing work. Because oddly enough, the time to converge is the radius of the network. It's a distance vector protocol. And as long as you keep compressing the network, convergence is brilliant. If you let this flow outward, convergence goes to the dogs. So, you know, cluster up. These folk are good folk. You know, cluster up and BGP will thank you.
All right, thanks.
Any other questions? If not, thank you very much, Jeff.
Thank you.
Thank you. And so next up we have another Jeff, Jeff Schmid from Telstra, who's going to be talking about IPv6 in the telco cloud and 5G.
Feedback will.
Because of that.
Yeah.
If you want to walk.
Yep. Hi. So my name's Jeff Schmid. I manage a team of network engineers in Telstra who design and build IP carriage for wireless. So I'm going to talk about what's driving IPv6 for us, where we're at with our deployment for IPv6 in wireless, what challenges are lying ahead, and what else do we need to consider.
Handheld might be better.
Okay.
Yeah, 'cause you have to-
So as V4 addresses deplete, it'll be more expensive to expand IPv4 resources for us. And the pressure for us is actually on the private address space in the wireless domain with always-on devices and a network as big as Telstra's, there's a requirement to connect to all the various parts of Telstra. And without islands or pods of our network distributed around our country, it is one large routing domain. So it's difficult for us to manage that V4 private space. Dual stack is really a transition to solve that problem for us. We really need single stack on our wireless devices, so that we're only terminating devices with a V6 address, so that we can relieve the pressure off the V4 private space. We do a lot of NAT. We'd like to reduce that dependency on NAT, and as I said, it removes the need to regionalise the network, which would be quite difficult to do on our network now. So this is a high-level diagram of a dual stack solution where over the radio and transport network, we're running V4, which is tunnelling the V6 addresses, which are terminating on the wireless device. And as you can see, the V4 addressing will use NAT 6.4 to get out to the V4 internet, and V6 will pass through the platform doing the carrier grade NAT transparently. So we use different APNs. In wireless, it's an access point name, which is used to describe or treat traffic differently. Telstra.WAP is what we use for wireless devices. There's a piece of code called 464XLAT, which allows us to run applications which don't support V6 on a wireless device. And that 464XLAT code will translate the V4 address into V6 and allow us to run single stack across our network until we reach our platform doing the the NAT64 translation. Tethering's a separate challenge. There's lots of protocols that are running on devices like laptops that tether to wireless devices, so it's a bit more challenging to support a single stack over tethered devices. So far we're running dual stack on the iPads that run across our network. So we have made some inroads into V6 deployment. A lot of the main carriers like Google are running V6, so that attracts a lot of traffic to them as V6 traffic. So some of the manufacturers who build devices, some of them that are very common that people use, are mandating V6, so that's helpful for us. That 464 XLAT capability is not required on a device if the device is mandating V6. So this shows that Google's traffic is continually growing. This is in bits per second. If it was IP flows, it would probably be a little bit different. So other issues or other challenges we have in the wireless core is managing complexity. So this is a challenge, or describes a challenge we have with service chaining, where we're on a subscriber basis looking to direct traffic to specific services that users are being offered. And to do that today, we run a number of VPNs and policy-based routing to steer traffic to those services on a subscriber basis. And as the number of services are added, the amount of complexity is increased significantly. And as we move to a virtualised environment, that problem still remains. Also, you can see there that the architecture is changing as we move towards a virtualised environment where we're Sorry. The slide up there is not the slide. No. So just describing the slide in front of me, the architecture for the wireless core is now evolving towards a data center type architecture, which is quite different with not sure what I'm looking at. What we are moving towards is to solve this problem and remove this complexity with with VPNs and policy-based routing is a service chaining solution that is subscriber aware and flow-based. So OpenFlow is a candidate to solve this problem, but it's not necessarily the option. OpenFlow has some scaling challenges. So there are other mechanisms, but what this solution can do is on a per subscriber direct chains of traffic to the services that a subscriber is subscribed to. So a bit further. So with the data center architectures, we would like to use VXLAN so we can move a service to an alternate data center. So in doing that, we introduce, besides VXLAN, overlay and underlay solutions. EVPN solves some scaling problems. It also allows better load distribution. So we are continually, without wanting to, adding complexity. There's some challenges with V6 with OpenStack. The other item there that is adding to the complexity is automation. As we move forward, we are looking to automate services as we build them across the network. As we introduce, so automation requires an IPAM that can provide addressing to services as they're automated. So we've seen some challenges with IPAMs that can support V6. There's also some issues with the virtual switches. We see some challenges with NFV as well in this trying to manage large volumes of traffic. We believe that the user plane particularly is quite challenging if we're running hundreds of gigs of throughput through a virtualised environment. So I suppose the way to manage that is to start with signalling. IMS traffic are very strong candidates to move into NFV. So probably a hybrid of control plane running through an NFV and user plane running through physical platforms would be the option for now. CUPS is control user plane separation. So the industry is looking to further separate control and user plane traffic in the wireless packet core nodes. MCORD is about virtualising the packet core nodes in a mobiles environment. So I suppose what that's saying is that, again, that user plane separation from control allows an NFV deployment. There's also, I think, questions about carrier grade as we move to NFV. Running packet gateways and signalling platforms in OpenStack environments, and that sort of environment is at least adding additional vendors to the mix. So there's certainly going to be some challenges. This slide is showing that there's a capability called mobile edge computing, where the services at the edge of the network are being put into, or can be put into, compute environments as well. Things like the baseband functions at the base stations, but also there is potential to run content at closer to the access network for services that require high or low latency. So in the transport component, SRv6 looks interesting. There is potential to simplify VXLAN solutions. There's also a capability called network slicing, where the network can be split up into slices where the packet gateways and signalling platforms can be separated depending on the type of traffic, so that, for example, IoT traffic could be treated to a standard broadband service. So SRv6 is a candidate to support that, where we could more simply support traffic engineering through an SRv6 solution. So this is saying that, as I was saying before, the focus for us has been on the subscriber endpoints on the wireless devices. O&M networks can follow, and we have been doing a fair bit of work in that space as well. IoT is a consideration. Certainly there'll be large solutions with lots of devices. Typical corporate solutions today probably do run on private address space and V4 anyway. But certainly some customers will be looking for V6 solutions for IoT. And as I mentioned, network slicing will continue to put pressure on infrastructure addressing as we automate the building of those slices, which are really multiple numbers of the packet core. The automation systems will need blocks of addresses to configure those elements. So IoT, telemetry is driving. In some ways it's not really anything new, but there certainly is a lot more of it. Devices with large battery life and low-cost devices are certainly changing the industry. There's also systems that allow customers to control their own SIMs. But I believe that certainly at the moment there's a set of solutions supporting telemetry solutions, and I imagine that will continue to be the case as we move forward. One of the current solutions is L2TP, which is quite old and inefficient. LNS is not cheap, so they're probably not the way forward. Private networks options as well. There's also some points there about changing the architecture to run packet gateways as PEs to support VPNs. Fixed addressing has been a challenge for us, but as the packet gateways can also support state between them, then those problems are being relaxed. This slide attempts to show how slicing could work. So the bottom part of the slide is at the cell site, and the middle part is mobile edge computing, which is really a hop away in the local exchange. And the decentralised data centre is in the core cities of main data centre sites. So The third column there could be a mission critical slice where the content is served up closer to the wireless device, and a virtual packet gateway could run closer to the base stations. Whereas the second column there could be voice, where in that case the content or the application would always be centralised. Another couple of options in the mix. Lanes provides an end-to-end QoS solution, including the radio bearer. So depending on your goal, our goal is to remove V4 off the network entirely at some point, to reduce the requirement to do NAT, and the reference there to V4 as a service, I suppose, is suggesting that V6 is the network, and in specific cases V4 would be offered. So there's still a lot of work to do for V6 for us, but also there's also a lot of challenges around the evolution of 5G, NFV, mobile edge computing. So there's certainly quite a bit going on. Certainly going from 2G to 3G and 3G to 4G. The period ahead is certainly quite interesting. So that was it.
All right, any questions for Jeff?
Oh, it's back.
Yep.
Hi, this is Shaowen from Juniper Networks. So I saw a very good goal. Everybody talking about the IPv6 service provider, and you list a lot of very good candidate for those technologies. Have Telstra already decided which one is better? Because I saw question mark in your slides still. So for example, you mentioned you may select the VXLAN plus EVPN method in the metro part, backhaul part, front haul part. Then you also talk about the SRv6. So because if you have a VXLAN EVPN, which is quite different with SRv6, totally different things, which one you select? That's my first question. And even the second one is network slicing. It's really cool thing. You list all the different combination and for different use case somehow. What exactly the network slicing you are looking for? Are you looking for one boxes simulate multiple network topology? Are you consider segment routing with flexible different calculation correct rules for different topology, or you really use logical system or somehow on the edge system? And can you share more detail on that one? My second question. Thank you.
The question about VXLAN, at the moment we're working towards VXLAN. So SRv6 is fairly, I suppose, new. But I suppose the attraction with SRv6 and probably over segment routing as well is that it's not reliant on MPLS, and to potentially have a SDN controlled traffic engineering solution to support the network slices does appear quite attractive.
Okay, thank you.
The second part about network slicing. So really that's all introduced along with NFV. So that allows you to build packet gateways and signalling platforms independent per slice. And one slice could be focused on mission critical and minimise latency for that subscriber, whereas others Other slices will have different characteristics. Yeah.
So the thing is, for network slicing, you can do a different way. You have a dedicated box for each individual slicing, or you you have one boxes that you can cut into 4 or 5 pieces here. And another one is you leverage the common protocol like a second routing, but you put a different calculation rules for different slicing. You have a different paths somehow. So which way you
So
want to select?
NFV will mean that we can run multiple slices on the same compute environment. Yeah.
Okay, thank you.
Yeah.
Jeff?
I'm just curious because I sat around for years as they did mobile IPv4, and then for even longer as they designed mobile IPv6. And the whole idea of that particular work in the IETF was a structure for mobility that didn't rely on fixed segmentation of network into VPNs or slices or anything else. It was just a straight datagram roaming protocol. Why the fascination with putting circuits, slices and state in the network? Is it the gene pool of the carrier and it's just that's the way you are, that's the animal that your genes say that you are? Or is there a real reason why that kind of datagram style technology for mobility, the IETF just got it wrong, which I must admit would surprise me, but I'm curious to understand why there's such a disconnect between all that work that went in developing a mobile datagram protocol and all the work that's going into segmenting and slicing in the network to deliver much the same outcome.
I mean, I think the work we're doing with V6 is really around solving the pressure we have on private address space. So the slicing part is really quite separate, really. Is that aligned with what your question is?
No. Right now, you seem to be suggesting that you want to slice the network up and do some bits for this kind of content, some for that kind of content, this kind of VPN, so the network corrals the traffic because you have some kind of interaction between provider, client, and what they're doing. Whereas what we see in a whole bunch of other environments, including the application space, is the use of protocols that hide what they're doing from the network. That, things like QUIC on UDP offer you no clue. And as a carrier, you're kind of going, I have no idea. I have no idea what to do with this traffic. I'll just put it in the bucket and pray. And this reaction of putting more and more segmentation and state in your network is a reaction that seems to come back from the dim dark mists of telephony. And I'm just sort of having this kind of moment of, why didn't this industry really take mobile IPv6 seriously? Was it just the ravings of lunacy, or they just didn't want to do it? No ideas?
Yeah, look, I think slicing is fairly new, and I don't know that it's been adopted a whole lot around the world. So it is it's a possibility, so it can be done. There are certain applications that might demand having the latency where if it's mission critical, you're running content close to the base station. 5G is demanding, 1 millisecond parameters and ultra high availability. So, look, I think it's whether slicing is popular and is deployed everywhere. I think it's still a little bit early to say, but it's certainly a capability that's interesting and maybe useful.
As a carrier, it's interesting to you.
Well, it's maybe useful. Yeah.
Okay.
Yeah.
Thank you.
Hi, Ketan Talaulikar, Cisco. I do agree with what Jeff said that we probably don't want to go to the telephony time when we had just circuits and so much state in the network, really, especially with 5G scale and all. But there are solutions and ideas being worked out where we don't need to do that kind of a state in the network, kind of like pin down circuits, but we still have slicing and all the SLA aware services that's there. So that is being worked on as well at the IETF. So it's not just because we say slicing, it doesn't have to be in the old traditional way of doing it.
Okay.
Any others? Looks like no. All right, so thank you very much for that, Jeff. Thank you. And so our final speaker, Kireti Kampela, who's going to be talking about self-driving networks for service delivery.
So this works? Okay. All right. Thank you. Thank you, Philip. Yeah, I'm not a Jeff, and I didn't work for Telstra either in the past or currently, but I'm still in this session, so you'll have to bear with me. I'm going to take this conversation in a very different direction, where Jeff Jeff Houston talked about the state of the internet for the last 24 years, and he has lots of data. And Jeff Schmidt talked about slightly, what's happening today and what's happening in the near future. I'm going off completely into La La Land, and I'll describe a future that might be. By the way, for those of you who are confused, just to make sure you're not confused, anytime someone says SDN to you, here, self-driving networks. You know, all the other stuff, forget about that. It's self-driving networks. So let me start with cars. This is a Benz patent motor wagon from back in 1886, so pretty much 130 years old. And it was, a lot of people thought it's just a horseless carriage, but it was a big change. And it started off life being very, very difficult to drive and very, very manual. But we went on from that to, I'm looking at this, I'm looking at that. We went on to add a lot of automation to the two cars. And this automation consisted of, instead of starting with a crank, we used an electronic starter. Instead of manual transmission, in the US, it's all automatic transmission, which basically means you can drive with 1 foot, and you don't have to have that coordination between the left foot and the right foot and your hands to manage those difficult things called gears, which actually I used to love, but now I have an electric car and there are no gears. Okay, so that matches, okay, fine, yes, we're good. We went from manual control of the engine to cruise control, to adaptive cruise control, to intelligent adaptive cruise control. And basically what this means is you can set the speed to whatever speed you think is safe, and then the car will maintain that speed. It used to be the case that if you say, I want to go 120 kilometers an hour, it will just stay there, and even if you're like 2 centimeters from the car in front of you, it'll try to continue at that speed. With intelligent cruise control, it actually uses a radar to keep a certain distance. We went from manual braking, where when you press the brakes, you had this mechanical coupling to the brake pads against the wheel, to anti-lock brake systems, which basically when you hit the brake, you're telling the car, I would like to stop when it's safe, but take your time about doing it, figure out whether there's slippage going on, and so on. And manual steering to automatic steering, manual parking, so the Manhattan-style parking where you reverse into your parking spot. Well, you now have cars, you push a button and they will do all of that. They don't unpark, so that becomes a real big problem when you've got 6 centimeters in front and 6 centimeters behind. The car got you in there, it won't get you out, and you've forgotten how to do this. But these are actually really good innovations. They make driving easier, they make driving safer, they make driving more convenient. If you have a lot of long distance driving, now all 3 monitors match, so this is perfect. Oh, yeah, we're up. I gotta stand a little bit here. Yeah, so these are really good. They've taken us a long way forward in how you drive cars. But the question is, are we done? And I mean, at this point, you know the answer. I've been giving this talk for a couple of years now, so the punchline has sort of been given away. But the punchline is, we had this DARPA challenge back in 2004, DARPA being the Defense Advanced Research Project Agency, said, build a fully autonomous car. I have no clue how to do it. You guys, smart guys out there, just go do it. I will help you. I'll create this 240-kilometer course in the Mojave Desert. It's on a freeway. There won't be any other human-driven cars, just the robotic cars. I will help you by offering a prize of $1 million. So go for it. And in 2004, when this was done, there were 25 teams, and the best they could do was about 12 kilometers. But in 2005, they redid this, and out of the 23 teams that took part, 5 of them managed this. Actually, a 6-team managed, but they took more than the allocated 6 hours. So there's a huge progress in the space of a year and a half. And so then they had an urban challenge, drive a 96-kilometer course, but now it's with traffic lights and stop signs and human drivers. And again, 6 cars completed this. The reason I bring this up is by having this kind of a vision, you can really move the industry forward in amazing ways, but you can also have this impact that you may not expect. So in particular, there's this whole thing that instead of having drivers, you now may just want programmers. You want people who program the car how to drive and monitor the car driving, and eventually there are no drivers in the cars. So much so that in the US, the Congress passed a law that said, because there are these, I don't know if they've passed it, but they proposed a law where instead of having this state and that city and that other municipality saying it's legal to have a self-driving car, they wanted one for all of the United States, but they said no trucks. Because, you know, not having drivers means a whole bunch of people lose their jobs. So this is the kind of impact if you go for these. I mean, you have this crazy idea, and then you go and you see that the technology is possible, but then the impact comes out. So you know this now. There are, in fact, much more than the Waymo car. This is an older slide, so it's a Google car. There's no pedals, there's no steering wheel. This is not an incremental improvement. This is a massive step forward in driving. So the question for me is, can we do something similar in networking? And so I proposed a networking grand challenge. Can you build a self-driving network? And by that I mean a network, you know, it just self-discovers all the components, it configures them with some basic configuration, it figures out how its links and how its components are doing. If something is not working, it'll correct it, it'll detect customers, it'll provide them with the right kind of service, it will diagnose when things are not going well, and of course it will report out, because at the end of the day, you need someone to make sure that it is doing what it needs to do. So the idea here is to free up people to work at a higher level. So instead of being down in the details with, and Jeff will throw something at me, but with BGP policy and why my prefix is doing this instead of doing that, and what's happening with my AS paths, you'll step back and say, make it happen, and the network will just work. But joking aside, the idea is also to get to a much more agile network, a network that will respond to things in real time, and maybe even anticipate what the customer wants, maybe even see patterns in how people are using the network, and accommodate the network to do that. And maybe the most important aspect of this is intelligent response to security breaches. So a challenge is, can you build a self-driving edge network, a self-driving network where you offer the services and it improves service agility and gets you to this proactive maintenance. So it understands that, hey, there's a line card here that's showing signs of failure, or there's a transponder there that needs some work, may fail in the next 3 or 4 days, so let me go and fix it or replace it before that happens. Or, hey, there's this traffic pattern that's changing, and so people are going to see, not that they already have seen, but they're going to see increased latency, so let me go make some changes. So get to the point where you're proactive instead of being reactive. And then here's a part where, coming from the US, is completely natural and normal for me, but some of you might object, where the network snoops on you, understands how you behave, and says, hey, I know how you use the network, and I'm going to sort of adapt to things because I'm aware of how you use the network. Well, the impact of this is you'll need new skill sets. So yeah, you know BGP, yeah, you know how to do all these policies, but no, that's old hat. Now you need to know how to tweak the AI to work the BGP to do the right thing. Or instead of having firewall rules, how do you look at things like anomalies? And so this is normal behavior. Now there's a spike or a drop in traffic. Why did that happen, and how do I fix it? So there's going to be these changes in how you think about the network, how you think about the people that you hire to run the network. But there are also going to be a whole bunch of possibilities opened up. And that's one of the things that I'd like you guys to think about. So while this technology is not here yet, I mean, we have lots of pieces. If it does come here, how would you completely rethink how you build networks? So for example, the 2020 Olympics that Japan is preparing for, and NTT and KDDI, they're actually doing a lot of work starting. Actually, they started in 2015, thinking about how they would do it. Imagine that instead you could just walk up, oh, the Olympics start tomorrow. Let me just have this truck full of equipment. I'll go and drop it at the stadium. They'll self-organize. They'll figure out where to put the radios, where to put the different equipment. And then as Olympics are running, they'll find that there's this corner that people are tweeting a lot and live Facebooking things and so on. And so I need to put more bandwidth there, and this other corner where people are old-fashioned and actually watching the races and talking to each other. I don't need any bandwidth there. This kind of live response to things. And then, of course, 2 weeks are over. I don't need the network anymore. The equipment just goes back on a truck and goes somewhere else, rather than doing a 5-year planning cycle for, hey, there's this big event. So how would we do this? So here are 5 technologies that I think are important: declarative intent, telemetry, correlation, automation, and decision making. So let's start with declarative intent. If you get into this Google car and get into some of these newer cars that people are experimenting with, you don't have a steering wheel, you don't have pedals. What could you do? Well, you have a little screen that says, where do you want to go? And maybe you can give it some hints about how you want to get there. Oh, I don't want to pay tolls. I want the route with the least smog in it. I have a Leaf, which is, I'm very sensitive about my battery. So yeah, find a route with the least usage of battery. Here's the creepy part. Again, from the U.S., we don't even think twice about this. We've got Google snooping on us. We got the NSA snooping on us. Is this being sent anywhere? Yes. Oh, undo the last couple of remarks. But imagine that the network understands how you use the network. Imagine in this case it's a car. The car just taps into your phone through Bluetooth and says, oh, you have an appointment at the Starbucks in 10 minutes, I'll take you there. Or imagine that every day it knows that you wake up in the morning you get into your car at 7, you take your daughter to school, and then you go to work and you come back. You don't even have to tell it. It knows how you do things. So that's the declarative statement. So if you take this to the network, imagine that you could just say to the network, make my customers happy, and it would just do that. Well, we don't quite have that, but we have this thing for a data center SDN This is the old-fashioned SDN, software-defined networks. You specify what your networking requirements are, where you want your VPNs or where you want your closed user groups. And it just happens automatically. When a new VM, virtual machine, shows up, it is automatically connected to the right VPN. If the VM moves, all the policies move with it. Or imagine a wide area network where you say, this is the kind of connectivity I want, these are the latencies I need between point A and point B, I want this types of resilience, make it so. So, if you could work at that high level and have the network just do the right things under the covers, that's what the game behind declarative intent is. Telemetry, we saw lots and lots of data from Jeff, and going back 2.5 decades, that was pretty cool. But imagine that you could do that for a lot more things than BGP. You could get real-time statistics. You're not SNMP probing all the time, but it's flowing to you. So you basically configure what we call sensors and say, measure the traffic on this interface, measure the power coming out of this transponder, measure what's going on with the FIB or with the routing engine, with the CPUs, and just send it to me every 10 seconds, every 5 seconds. And it would just flow to you, you'd gather it, you'd make beautiful slides. Jeff would tell you how to plot it and whether to put an exponential through it or something else. So you need this networking big data as a starting point to do the next thing, which is correlation. So I have this network, and I've got these users at one end, I've got clouds, and I've got peers, and I've got IGP information, I've got path information, but I want to get down to what are my users doing and how is the state of the network affecting them? What happens when a particular user is trying to get to a particular cloud or they're trying to get to a particular peer? And should I be going to a different peer because that peer costs less or they have better latency or they have a more resilient path? So the idea that you can get to, if you have this high quality real-time data, you can go from an IP address that Jeff loves so much to, no, it's this particular subscriber of mine talking to this particular peer, going over this path in my network and encountering this kind of congestion or this kind of latency. And then once you're there, you then say, okay, for this user, this is the normal behavior, so now I can see anomalies. Or for this peer, this is what I should be expecting, and so maybe I should up my peering relationships. So if you have IPFix information, you have a source IP, a dest IP, and port numbers that excite us geeks so much, but the business guys are going to look at that and say, what does it really mean for my business? Automation, and we've talked a lot about automation. Jeff Schmidt mentioned automation in his talk. So here is a potential networking stack from a vendor that I have no idea who it is. But the thing that I want to point out, I've carefully scrubbed the slides. You can look actually, there are a couple of things that you can see, but mostly they've been scrubbed. There are these automation frameworks, Python, Chef and Puppet, Ansible, SaltStack, and then there's these frameworks like PyEasy or RubyEasy where you can use Python to say, this is what I want to have happen in my network. And of course, there's NetConf and there's RustConf, and the idea of having a way to talk to the box that I don't have to be sitting on the CLI all the time. So automation is important, and I'll tell you why and how in the framework of self-driving networks. But the final component of this, the first four we have already. The final component we're in the process of building, which is how do I make decisions in the network? Do I use rule-based systems or do I use machine learning? And one of the things I want to emphasize to you is when I got into this because I think there's a huge there's a huge place for machine learning in networking, but we're not doing it. But I don't want this to be a talk about machine learning and about bringing new technologies to networking. I want to solve a real problem, which is the way we do operations in networks today is very reactive, very slow, and so I want to get to a place where the network can run itself. And rule-based systems are really good because when the number of rules are small, they're simple, the interactions are easy to figure out. But eventually, I think we need to get to machine learning. So if you think about the 5 stages of self-driving, you can start with completely manual networks, and hopefully most of you have gone a little beyond that, at least to the point where you're gathering data from the networks and visualizing it and seeing where the hotspots are, seeing where you need to be a little more proactive about things. But you want to get to the place where you can start making predictions and saying, this is what I need to do, this is where I will need some work. Whether the predictions are about, in a week, this transponder will fail, so let me do proactive maintenance, or in 3 months, this is what my BGP prefixes will do, or this is what my traffic will do, and so this is what I need to do to make sure that everything's good after that. To the point where the self-driving system, can actually make recommendations. Here's what's going on in your network. If I were you, this is what I would do. Or looking at your logs and saying, okay, you've got 1 million lines of syslog. From those 1 million lines, here are 5 things that I would point out. And this is what I would do if I were you. And the reason why I mention this is, we'd love to get to the point where the network actually runs itself and is fully autonomous. But if you think about cars, you can get to fully autonomous cars, but a lot of people are saying, let me get to this intermediate stage where the car will mostly drive itself and center itself in its lane and so on. But once in a while, it'll tell you, hey, I don't know what to do in this situation, take over. And you're dead. Literally, you're dead. That's what happened to a certain person who was driving a Tesla and watching Harry Potter or something, and the car was not able to deal with the situation, and the person was not alert enough to take over. In networks, typically you don't have to react in milliseconds, or at least when you do have to, we've already automated that. And typically it's not life or death. So if we get to the point where the self-driving system can do a lot of the work and actually run the network reasonably well, and when it can't, it'll say, here are 5 things I would do, but Mr. Human, you know this a lot better, you have better intuition, you take over. I think that works. All right, so if we want to do this for services, what does this look like? So here's a very simplified version of what a self-driving network would be. It's basically a closed-loop system, or almost a closed-loop system, where you have telemetry coming out of the network, you do some analysis on it, you make a decision, and then you implement that decision back into the network. And that's where you would use automation or other ways of taking your decision and enforcing it in the network. And why I say it's almost closed loop is that this is all guided by this intent. So you tell the network roughly how you would like it to run. I'm going to make some statements that people might want to throw things at me, so I'll see if I can duck. But if you were to tell the network, here are the customers who are really nice and pay me a lot of money, and here are the customers who are not so nice and don't pay me quite as much. Here are the peers that I have a really good relationship with, and here are the peers that are really painful and they drop a lot of traffic. Here are the clouds that I want to work with. Here are the clouds that the government makes me connect to, but I don't really care about. Basically, you take these business decisions and you tell the network, I have finite resources, optimized for them. That's one way you could think of intent. And that's a very high-level way of running your network. You could get much more granular and say, I know that this customer has this kind of behavior, so I want you to make sure that when they do their backup at 4 in the morning, they have enough bandwidth for that. There are many ways you can express the intent, and there are many levels at which you can express it. But the intent is your high-level way of telling the network how you want it to run, and then it goes off and does its thing. So I do want to mention that this, when I talk about self-driving networks, a lot of people say, but we have zero-touch provisioning. It's beyond the initial provisioning, beyond, oh, I plug this device into the network and it's now a member of the network. It is the full life cycle of managing the device. And in the case of services, it's a full life cycle of managing the services. So what would service networks look like? Basically, you're doing the same thing, but the telemetry is service-oriented telemetry. The analysis is, how are my services doing? Are my customers happy or by and large happy? What do I need to do to make sure the service lifecycle is the right thing? Do I want to get proactive and tell my customer, here's how you're using the network. If you were to increase your bandwidth here, or if you were to subscribe to this other service, this is how it would improve what you see. And then, of course, you need to do the service creation and the service management, so you take the actions in the network. So specifically, you want to be able to self-monitor, self-diagnose, and self-correct if there's something going on in the network. So this would apply to BNG and subscriber services, so mobile subscribers as well as fixed line services, where you get all this telemetry from the network, and you say, okay, this is my subscriber intent, so this is how I want you to run the network. You could do this for your peering systems, where you have an endpoint going to one of those 4 sites that Jeff mentioned. There are only 4 sites in the network, in the universe. But I'm trying to get to them, and which peer do I want to go through to get to one of those 4 sites? Or I'm trying to get to one of these 3 clouds, and which cloud should I use? IoT. One of the things that really scares me about IoT is we're going to have a huge number of devices out there, and many of those devices are going to be weak and not very well thought out from a security point of view. So it's going to create potentially a huge security nightmare for people running the network. So if you don't like the expansion I gave you for SDN, think instead self-defending networks. That works too. But here the idea is that you use the regular behavior of a device. So if a device goes out to the DNS system once a day to say, let me just confirm that my server that I'm trying to get to is still at the same IP address, and suddenly it starts going to that DNS server once every 2 seconds, you know that there's been a change, and so you know that you might want to do something about that. So if you did this, if you got to the point where you were running a self-driving, you had a self-driving network, especially from the service point of view. And the reason why I mentioned services, you could start this in many places, but here's a place where you could have a definite impact on your customers. Your customers are happy, your CFO is happy, eventually, trickle-down economics, you're happy. I come from the US, we believe in trickle-down economics. So here's why you should be doing it. And like I said, this is a closed-loop system, and ultimately you want the network to completely run itself. So conclusion. Basically, I think we need a bold vision, and I think we do things incrementally a lot in networks, and we wanted to take a small step here and another small step there. I think we need to take a giant step back. There are people who are going to be really upset that they've spent all this time learning how to, tune ISIS and BGP, and I know how all these policies work, and I can type ACLs in my sleep. There are people who have JNCIEs or CCIEs or whatever Arista comes up with. Yeah, don't throw them out the window. You need them, because when the AI takes over and actually runs the network, you need to tell it where it's going wrong. But eventually, you need to step back from that. So if we do this, we will find that there are these imperatives that say why you should be doing this. And here's a quote from OBS's, OBS being Orange Business Service. Basically, the CEO, Thierry Bonhomme, says, I cannot find people with the skill set I need. And by that, I think he means someone who knows how to run a network, someone who knows enough Python to write some shell scripts or some Python scripts, and someone who can make the network run much better. And so rather than try to solve that problem, we can step back and say, how about I let the network run itself? So yeah.
All right, thank you. Any questions? Any questions for Kiriti? I think we've just exhausted everybody today, haven't
so,
we?
yes.
Or they're being saved for the social event. So,
I don't know if you're coming up for a question.
question? Oh,
you
great,
are.
excellent.
So I've been working in a self-driving network now for a while,
Oh, cool.
complete with ZTP processes. And my impression is that they're so monolithic at this point that we haven't even put in any kind of adaptive feedback in them. They either succeed or they fail. And that's just one comment. I appreciate your input on that. But more importantly, where's the 245-kilometer course in the middle of the desert? And where's all that test bed? And where's my $1 million prize, right? So how are you going to get people to actually be interested in this when they've got running networks and product groups that are, burning down the house to make sure that you don't crater the network when you're introducing new products, et cetera?
Yeah, no, good questions. So let me start with, people have done, and different groups are at different levels of automation. Some people are really, at the early stages of it. Some people do a lot more automation. One of the things that we've done is this thing called event-driven automation or event-driven systems, where I have a few things that I know happen quite often in my network, and if they happen, I have some automated response to them. So you're creating these mini loops. And so one of the things that we're thinking, there's this big problem, and you said, where's my 240-kilometer thing that I start with? So we're looking at this big closed loop system and saying it actually consists of many smaller closed loop systems. So what if I had a closed loop system that looks at SLA fulfillment? Am I doing well or not? And if I'm not doing well, even if I don't take an action, I raise an alarm saying this SLA is not working. I have another closed loop system that says I'll make sure my LSPs, back in the day I was an MPLS guy, I still am an MPLS guy. So I'm looking at my LSPs and I want to rebalance them because I need better latency or more bandwidth somewhere. So but then you start connecting these. So, my SLAs are not working. Maybe I need to go to the LSP system and say, make this change. So you start with these small systems, and if you build those systems, then you start interconnecting them. And then you end up, and then there's also this egress peer engineering, which is a whole separate thing, and say, how does my SLA fulfillment relate to my LSPs, and how does that relate to my egress peer engineering? And now I start looking at more of an end-to-end thing. So I think you start small and then you build. So that's what I would say. But I will acknowledge that there have been things, not just ZTP systems, but self-organizing networks in mobile, which is primarily thinking about how do I optimize radio performance. But they are looking at closed loops for doing such things. So I think we have building blocks. But I want to get to the point where network operators are really, I used to have a slide where they're sitting in a hammock, sipping a Mai Tai. And yeah, they have a screen that says your network is fine, your network is fine, your network is fine, you need to do something. But most of the time, they just let the network run. Alain.
From ICANN. Have you looked at the proposed regulation in Europe on e-privacy?
That's why I said 17 times I'm from the US. I don't know what you're talking about. Yes. There are, actually, it is a serious problem. And I mean,
No, it's a serious question.
I'm not being facetious. Big data, and so I call this networking big data. You need a lot of data to be able to do things. And machine learning algorithms, especially, are really poor until you have lots and lots of data. When you look at providers, so I've got AT&T here, I've got Telstra there, I've got Singtel there. They don't share a whole lot of information with each other, and if they share stuff, it's through the policies of BGP. So there's kind of sort of So we don't get big data there. But then on top of that, what you're saying is even more important, that I can't even share across countries, because in Europe, people want to keep things within the national domain. So how do you get to the point where I have enough big data where I can say this is how things work and this is what is happening? It's a big problem. And
It's actually worse than that, because my reading of a proposed regulation is correct. Any data or metadata related to a specific communication between two users, if one of them is from Europe, has to be discarded as soon as the communication is over. Meaning that you cannot use any of that to do any learning to adapt your network.
Can we export the NSA to you guys? No, it's a problem. And that's one of the things about machine learning is, deep learning specifically. There are other machine learning algorithms that don't need quite as much data, that may not be as accurate and so on, but at least they can start working much more quickly.
Okay, last question.
Yeah.
Kyoto Labs. So my question is technical. It's a great idea to automate processes of internet service providers. You select a goal, and the system after that just selects, configures, and so on.
Yes.
But different ISPs may have different goals, and even conflict goals. Don't you think that we can end up with robots fighting each other?
It's better that the robots fight each other than they fight us. But Elon Musk says we should stop working on AI because they're going to kill us, or if we don't have the right regulations. Actually, probably this is why we have BGP and policy. That's what keeps the robots from fighting each other directly. They can influence the policies, and of course they can do that and then create some crazy loops in the network or very suboptimal paths. That's why when I said in this in the list of things, I don't know if I can go backwards. I don't know if I should even try. Well, basically, here, recommendation. I think for a long time we live in the stage where I have massive amounts of data. And in fact, if you look at operators today, they discard most of it because they just can't process it. If you have these systems process massive amounts of data and say, here are 5 recommendations, or here are 5 things to think about, to look at.
Yeah, but if there will be different players, different goals, even conflict goals, both of them will press accept and they will just may go to some devastating results.
It's possible, yeah. But I think where we are today, where we run the networks...
Robots that are talking to robots, maybe?
Sorry?
Robots that are talking to robots, maybe?
Yeah, it could happen. But I think that would be a step forward, because then we have to come back and figure out how to get the robots to adhere to a more global goal. So it comes back to intent. And I think where we'll start with intent is what's best for me, what's best for my network. And if that intent is in conflict with your network, we have this conflict, and then we get up a higher level and say what's best for the continent or what's best for the planet. Or if you really want to go to Mars, then what's best? You know what IP stands for, right? Interplanetary?
Okay, thank you.
All right, thank you.
All right, so thank you very much, Kiriti. It was great. Excellent. So I just want to wrap up the session. We're running a little bit over time, but then we start a little bit late as well. So this was the end of the first APOP session. We have another one tomorrow, starting at 9:30. 2 interesting talks. They're quite long ones compared with what we had today, so we'll just have the 2 tomorrow. Right now, we have a routing security buff in this room, so if you're interested in routing security, please stay in your seats. If you're not interested in routing security, then I'm sure there are lots of other things you can do. Don't forget the social event this evening. That's starting at 7 o'clock. We don't have far to go. It's just out on the lawn of the hotel. So either enjoy your buff or see you this evening.